All right, lesson 7, general pyramids and cones and their cross-section. Today's goal is, well, the opening exercise goal is to remind you guys of the parent category of general cylinders, how prisms are a subcategory under general cylinders, and then how to draw a parallel to figures that comes to a point. Some of the figures that come to a point have polygonal bases, while some have curved bases. So let's go ahead and do this really fast exercise, okay? It says group the following images by shared properties. What defines each of the groups you have made? Okay, you have all these pictures in front of you, so I need to grab a fresh slide so that I can actually make some groups. So go ahead and look at your pictures, and I'm going to make them disappear. All right, if we look at, let's just call it group A. Let's call group A general cylinders. Which ones are general cylinders? Okay, let's say that is going to be image number 1 and 6. Okay, if I look at number 1, it has a funny curved base. And number 6 has a funny curved base. And then the cylinders don't have a point at the top. Their bases, the top and the bottom base, are parallel. Okay? Group B, let's name that one prisms. Prisms are going to be images 2 and 7. Now, if you look at image 2, it has a triangular base and some lateral faces. But we have right edges, right lateral faces to the base. And then 7 is the same. I've got a base that's parallel to another base, and then the lateral faces that are perpendicular to the bases. Let's try group C. Let's name that one figures that come to a point with a polygonal base. And that would be image 4 and 5. If you look at image 4, it looks to have a square base, and then all the lateral faces come to a point. And image 5 has a pentagon for a base, and all the lateral faces come to a point. And then we have group D, figures that come to a point with curved or semi-curved base. Let's say that is image 3 and 8. Image 3, funny curve with some straight edges too. Image 8 looks like a swimming pool with a teepee over it. But those are our main groups. Okay, we're going to talk through, oh, for goodness sakes, we are going to talk through definitions of cone and rectangular pyramid. We're going to do that in relation to the opening exercise. Okay, so I've got lots of drawings I'm going to have in the next few slides, and we're going to really get some nice definitions and some nice vocabulary for them. If you could write down your own definitions, that would be awesome. But let's go ahead and talk through some more. So first we're going to look at, let's see, image 4 and 5. So we're going to talk through image 4 and 5, which we called group C, which was, we had figures that came to a point and had a polygonal base. All right, so image 4 was a rectangular pyramid. What would be your definition of a rectangular pyramid? Okay, think about it for a minute. And then we have images 2, 4, 5, and 8. You have all those in front of you. Those are all general cones. Okay, what's your definition for a general cone? What do you think? Okay, let's look at the next slide. Okay, here I have a rectangular pyramid. So given a rectangular region B in a plane E and a point V that's not in E, the rectangular pyramid with base B and vertex V is the collection of all segments VP for any point P in B. But I need a rectangular region. So these two drawings on this page are not a rectangular pyramid because I don't have a rectangular region in B. Okay, the region I have here is a funny swimming pool shape. Or, I don't know, a polar bear. What do you guys think it looks like? It's interesting. Okay, so rectangular pyramid, we would have a plane E and a rectangle in E and a point V not. Okay, not in your plane. And I've got all the segments VP. These are all points P in your rectangle B. General cone, let B be a region in plane E. So I've got B is a region in plane E, and V is a point not in E. The cone with base B and vertex V here we have is the union of all the segments VP. So these are all points P down here where your segment hits the region. Cool? There is your definition. Here we have our rectangular pyramids, and let's look at this. So you've seen rectangular pyramids before. Look at the definition again. You have it on your previous slide, it's actually in your paper on my previous slide. Look at the definition and compare and contrast it with the definition of the general cone. It's all about the base. The definitions are really the same. The only difference is that a rectangular pyramid has a rectangular base. Okay, I've got this base here. And the general cone had the funny polar bear base. Basically, the general cone can have any base. So the general cone can have any base. But a rectangular pyramid has to have a rectangle for a base. A general cone with a disc as a base. You know, disc is another name for a circle. A general cone with a disc for a base is called a circular cone. So you've got a circle for a base and all of these points here connecting at point V. A general cone with a polygonal base is called a pyramid. General cone with a polygonal base is called a pyramid. We're getting all the different types of general cones now. Examples include a rectangular pyramid or even a triangular pyramid. Okay, rectangular pyramid is what we see up here. A triangular pyramid, all you have is a triangle for a base. And all of these points connect up here at V. That's an awesome drawing if I say so myself. A general cone whose vertex lies on the perpendicular line to the base and passes through the center of the base is a right cone. We have that example right here. Okay? A general cone whose vertex lies on the perpendicular line to the base, and it passes through the center of the base. Right there, we've got right into the center where the two diagonals meet. That's awful. Okay, where these two diagonals meet is the center of the base, and the vertex makes a perpendicular point with the base. I have a right rectangular pyramid. Here I just have a rectangular pyramid. And here I have a triangular pyramid. Pretty cool. Let's see, what else do I need to tell you? How about a right circular cone? So I have a circle. Where do you think the vertex is? The vertex has to come through at a perpendicular spot and through the center of the circle. And then we have all these points that would go up to the vertex from everywhere around the circle. That looks awesome. All right, let's go on. All right, first question. Name a lateral face and edge in figure 5 and explain how you know it's a lateral face. First of all, let's look at it. I have a triangular region, AVB, let's highlight that, AVB, oops, triangular region AVB, which is defined by a side of the base AB. Which you see right there. Oh, for goodness sakes, sorry. And vertex V. And is an example of a lateral face. My lateral edges, once I tell you what they are sort of easy to figure out. Let's get a new color. Green. Lateral edges are all the edges of the figure, okay? Lateral edges, I've got everything that goes up to the vertex. Those are all lateral edges. So now you know the pieces and the parts of a rectangular pyramid and a general cone. So now we have to look at the cross section and how it's similar to the base. I just said the cross section is similar to the base. Okay, remember we have similar rules with proportions, area, etc. Okay, we have to dig back just a little bit to our similar rules, okay? if we look at this general cone, I have plane E prime right there. Hold on, let's see if I can make this bigger. That'll work. I have plane E prime, which is parallel to plane E. And this plane is between point V and plane E. So this is parallel to V and plane E. So it sort of gives us a cross section. Okay, the intersection of the general cone with E prime gives us a cross section B prime. So B prime is a cross section, and we learned in the last lesson that cross sections are parallel to your base. B prime is a cross section, okay? So we can show the existence of a dilation. Here we have a dilation that maps B to B prime. Okay, it's a similarity transformation, remember? So dilations we studied a while ago. We studied them in the plane, in just 2 dimensions, length and width. We have not studied them in 3-dimensional space yet. So here's our first try at 3-dimensional dilations. A dilation with 3 dimensions okay, we still will have a center. We're going to call the center O for now, and a scale factor. We'll just call the scale factor R. That's a scale factor we seem to like to use. So I have a center O and a scale factor R, and we define that the same way as when we worked in a plane. The dilation maps O to itself, it stays, and maps any other point X to the point X prime on ray OX. Remember when we did scale factors, if we were scaling down, we would be in between O and where we started. If we're scaling up, we would go past the point. Let's see. So let's do this. The dilation maps O to itself and maps any other point X to the point X prime on your ray OX, so that OX prime equals R times OX. And if R is bigger than 1, we're getting bigger, and if it's less than 1, we're getting smaller, right? All right, let's see if we can try one of these to make it make sense. So example 1, we've made the claim that a cross-section of a general cone is similar to its base. That means the sides are going to stay proportional, and we're going to use a scale factor to compare them. So using the following question as a means of demonstrating why this should be true. So let's look at example 1. In the following triangular pyramid, a plane passes through the pyramid right there. plane passes through the pyramid so that it's parallel to the base and results in the cross-section A prime, B prime, C prime. If the area of triangle ABC is 25 millimeters squared, what is the area of triangle A prime, B prime, C prime? So we need to figure out our scale factor. And then if you remember, area doesn't scale just 1 to 1. We have to square with area. Okay? So let me get the highlighter out again. Okay, we're going to look at that line. That's what we're going to, and we just talked about in the last slide, our ray, and how when we scale something, we scale it along a ray. So our center has to be V, and our scale factor, we're going to use, oh, those are still highlighting, those measurements there. So our scale factor, we're getting smaller. Oh, for goodness sakes, I forgot to turn it off again. Our scale factor is going to be 3 over 5. Because if we look at VA prime, we're at 3. And VA, we're at 5. So our scale factor has to be 3 over 5. A dilation tells us that A prime, B prime is going to be 3/5 of AB, right? Since the cross-section is parallel to the base, we can say that all of our sides are parallel. Since the cross-section, we learned this in the last lesson, or 2 lessons ago, since the cross-section is parallel to the base, we know that, therefore, BC is parallel to B prime, C prime, etc. AC is parallel to A prime, C prime. And just like with A prime, B prime scale factor, I can do the same thing with BC. So my scale factor maps B to B prime and C to C prime. So I can say that B prime, C prime is equal to my scale factor times BC. I can also say that A prime, C prime is the scale factor times AC. These are all my really important discoveries. Okay, it's my takeaway, right? Now let's talk about the area of the triangles. Well, we remember from quite a few lessons ago that when we scale the area of something, the area would be equal to the scale factor squared the area of the other one. It depends on if we're going bigger or smaller. So in our case, what we're doing right now, we're going to say the area of A prime, B prime, C prime triangle is equal to, oh, for goodness sakes, I should count how many times I say that in the lesson. 3/5 squared times the area of the bigger triangle, ABC, right? So if we know the area of the bigger triangle is 25, the area of the small triangle is going to be 9. I forgot area again, or I mean triangle. Very, very fun. So based on what we know about the cross-section of the pyramid, we can determine the cross-section is in fact similar to the base and use that knowledge to determine the area of the cross-section. That was fun. Let's look at another example. In the following triangular pyramid, a plane passes through the pyramid so it's parallel to the base and results in the cross-section triangle A prime, B prime, C prime. The altitude from V is drawn, and the intersection of the altitude with base X, which is the original base, and the intersection of the altitude with the cross-section is X prime. So I have the altitude that's going through X and X prime, right? If the distance from X to V is 18, the distance from X prime to V is 12, and the area of triangle ABC is 28. So what is our scale factor? We used K in the last one. So our scale factor is going to be 12 over 18, which simplifies to 6 over 8. Well, I can do that again. 3, oh, that's a 9. There we go. 6 over 9, which simplifies to 2/3. I probably took too many steps in that one. Oh well. So there's my scale factor. We know that that the cross-section is similar to the base of the triangular pyramid. So I can say that the area of triangle A prime, B prime, C prime is going to be 2/3 squared, because when we are doing scale factors with area, we square the scale factor. Area of triangle ABC. In this case, we know the area of the cross-sectional triangle, that is 28, is equal to 4/9 area of triangle ABC. So 28 times 9 is 252, divided by 4 is 63. Let's do that. Let's show you all the work. 28 times 9 over 4 is 252 over 4 is 63, equals area of triangle ABC. It should be bigger than the given area, because the given area was the cross-section. So that's pretty awesome. All right, let's look at exercise 1. The area of the base of a cone is 16 and the height is 10. So the area is 16, the height is 10. Find the area of a cross-section that is 5, distance of 5 from the vertex. So I don't know what kind of cone it is. That's all right. The area of the base of the cone is 16. The height is 10. Find the area of the cross-sectional unit. That is 5 distance from the vertex. Okay, that drawing that I made is really, truly awesome, but it's okay. So I have the area of the cross-section. Is equal to, let's see, my scale factor is going to be 5 over 10. K equals 5 over 10, which is 1/2. 1/2 squared times the area, let's give you this, area of the original. So that is 1/4 times 16, which is just plain old 4. Units squared. Very cool. Okay, example 3, we're not actually going to do, but I want to make sure that we all look at this theorem, because we're going to use it in our problem set. The general cone cross-section theorem. If two general cones have the same base area and the same height, then cross sections for the general cones, the same distance from the vertex, have the same area. And that makes sense because they're scaled. What it's saying is if these have the same area, the same value, the same number, and the distance to the vertex is the same, then I need another color. Ooh, purple. So we just did, if two general cones have the same base area and the same height, then cross sections for the general cones, the same distance from the vertex, have the same area. It makes sense, okay? But we're not going to go through the proof for it, and that's okay. I need a black pen. The following pyramids have equal altitudes, and both bases are equal in area and are coplanar. That means they share the same plane. Both pyramids' cross-sections are also coplanar. That means they share the same plane. And they have equal altitudes. That means that the top is the same distance. So from here down is the same as from here down because they share the same plane. So the distance from the vertex to that plane is equal. Now we see that BC is 3 square roots of 2, and B prime C prime is 2 square roots of 3. Find the area, and the area of TUVWXYZ is 30 units squared. What is the area of the cross section A prime, B prime, C prime, D prime? So we're looking for the area of this cross section. All that means is the area of A, B, C, D is also 30. And our scale factor is going to be 2 square roots of 3 over 3 square roots of 3, or just plain old 2/3. So the area, what we're looking for is the area of A prime, B prime, C prime, D prime, which is smaller. So the area of that is going to be equal to 2/3 squared times the area of A, B, C, D. 4/9 times 30. 4 times 30 is 120. Divide by 9 is not even. Arg. Does anyone see my mistake? I did not copy those values down correctly. So rather than hide my mistake, let's go ahead and fix it. 2 square roots of 3 over 3 square roots of 2. Two square roots of 3 over 3 square roots of 2 squared times 30. 2 square roots of 3 over 3 square roots of 2 squared. Let's see, I'm going to square that and get a 4. Square this and get a 3 over 9 times 2. 12 times 18 times 30. Let's try that one. 12 times 30 is 360. Divide by 18 is 20. 20 units squared is my answer. Excuse the mistakes, but I feel that we can learn from them. And that's it. There's a lesson summary at the top of your problem set if you'd like to read through what we did. But this was a fun lesson. We'll try the problem set tomorrow. Good job.